It's my pleasure to introduce Saidapet Ramesh. He's a technical director of NPI DFT design quality team at NXP Semiconductor. He has about 19 years of experience spread across Intel, Qualcomm, and NXP in PC server, mobile SoCs, automotive edge, radar, frequency processing. His experience spans a mixture of roles in DFT, product test, yield, scan diagnosis, and failure analysis. He holds an MS in electrical engineering with specialization in DFT from University of North Carolina at Charlotte. Welcome.
Good afternoon, everyone. I hate to be between all of you on your lunch, but I'll try my level best to finish this session on time. So today we're going to be talking about the targeted screening of bridges with defect-oriented tests, which is automotive grade, which requires an automotive grade ATPG license from Tessent. So this is a list of co-authors and team members who really contributed to this project. And as you can see, it spans all the way from DFT to test product and failure analysis engineering teams. And this team is spread across multiple geographical locations as well. So I didn't put a slide for NXP, but NXP Semiconductors is one of the top 2 automotive suppliers. The market share keeps changing between us and one of our competitors. So we are all about zero defects. And we have multiple business lines, but automotive is one of the biggest revenue winners. And this topic is all going to be about how we constantly stay ahead to keep up with the new requirements for zero defects. So the purpose for this whole evaluation in collaboration with Siemens Tessent R&D team was to evaluate the layout-aware ATPG tests, because our current models, for bridge coverage, is totally based on the BCE values that we get from our NDetect, Tucket, and TD test pattern runs. And what we are observing is it's starting to not hold for the lower and advanced process nodes to keep up with the zero defect demand. And our automotive customers have started to shift from 0 DPPM to 0 DPPB goals now. So I'll go over why that has changed, and that is why we have to constantly stay ahead to keep up with the new demands. So today's presentation outline is we'll start with an introduction, and I'll give a brief introduction into DOT, defect-oriented test, then the interconnect bridge and open defects section of DOT. That is the primary focus of today's presentation. And then we will continue with the actual evaluation of the ICBO tests on NXP designs, followed by silicon fallout data review. And we will end it with the silicon debug and the limitations that we ran into from our silicon learnings. And finally, we'll just conclude the session. The introduction, like I said, our automotive customers are setting 0 DPPB goals. This is an old paper from 2018 at the European AEC reliability workshop, where one of our, BMW came and said, if we just stick to the less than 1 DPPM, 0 DPPM is on paper. In real world, it's really less than 1 DPPM that we all strive for. With the number of semiconductors per vehicle constantly increasing, and this is 2018 data, and we are it's 2023 now. So they are projecting that with the same old DPPM goals, they were anticipating 1 car failure per hour that they have to deal with, which is not acceptable. So that's why all our goals has shifted from DPPM to DPPB. And what we found was just relying on the traditional ATPG fault models, which only use port level test coverage goals and is not layout aware, needed some enhancements. And that's where this whole defect-oriented test from our partners, Tessent, Siemens, Tessent tool came. And we started integrating the cell-aware UDFM-based models, but that only covers the front end of line and middle of line defects inside cell instances. And they are, layout aware, but there was no targeted test generation that was happening for our back end of line vias and the upper metal layers. And the legacy bridging model that we had evaluated before was just too costly, and it was not layout aware. So just a brief introduction into DOT. it's more like a marketing pitch, but I just want to bring the audience up to speed if you haven't worked on DOT, right? It's completely the new DOT feature of Tessent enables complete physical defect-based ATPG, right, for the digital sea of gates. And it provides advanced defect-oriented fault models and is supposed to help achieve zero defects on automotive designs. Like I mentioned before, the traditional Stuckert and TD fault models only address the faults on the ports of logic. And the defect-oriented tests are mainly spread into 4 different categories. The cell internal defects, which is called cell aware. It's already very popular. I know the industry uses it a lot. Then comes the interconnect bridge defects that are modeled using critical area from layout. We'll be going over that at a high level. And then comes interconnect open defects with the same critical area based extractions. And finally, they also came up with inter-cell bridge defects between neighboring cells. So today's presentation, I just wanted to show a snapshot of the fault extraction views. The top portion is the cell-aware part, where we are using Tessent cell model gen to do the cell-aware model creation and UDFM extraction, using which we can do ATPG pattern generation. Then comes the interconnect bridges and opens, and the cell neighborhood bridges, which actually just reuses the LDB database, which is the layout database generated using the LEF and DEF files. So for all companies which already use the layout-aware diagnosis feature of Tessent, we pretty much just have to reuse the same LDB file and do the UDFM extraction for interconnect bridges and interconnect opens. And that UDFM can be used for pattern generation. So the third part is more complicated. It involves some additional steps for cell neighborhood bridges. We will not be covering that in today's presentation. We have to do the cell pair extraction first, followed by using cell model gen to do cell pair model creation. And then you get the final UDFM that can be used for ATPG pattern generation. So now let's just focus on the ICB and ICO tests, right? So what we are showing here is how the extraction is done, is using a new critical area feature that was defined by Siemens Tessent tool. The example shown here at the top for interconnect bridges is you see these 2 metal 1 lines running pretty close to each other, and you have 2 metal 2 lines also running close to each other, and they have their own secret sauce where they're paying attention to how close the same lines are running and how long is the proximity of the lines. So they do all of this and come up with a critical area based extraction for bridges. And opens is much simpler than bridges here. They pretty much look at a net, break it down into different segments between different metal layers and the via layers, and they start modeling opens. And they do a actual UDFM extraction using the LDB file. Now, again, a quick summary on the total critical area. The key thing to pay attention is everything is measured in what is called as technology squares. Technology squares is a sum of, technology square is the metal 1 width of the technology node is the 1 TL. And then with their calculations based on how close the metal lines run, they come up with this critical area based on 4.1 TS. In this example, as you can see, since metal 1 is running much closer to each other and it's also running longer in close proximity, so it has a higher critical area where if a defect were to land, it is going to cause a defect. And then on the right side, the metal 2, the critical area is a lot less than the metal 1. All of these pictures are taken from the Tessent Scan and ATPG Users Manual. Then a quick review of how the fault modeling is done. So this is the 4-way bridge model for interconnect bridge pattern generation. This is a simple example where they're showing a 2 input mux, and they do this aggressor-victim pair combinations. So in the top left side, what we have is you have the aggressor as the net A on the top, and the victim is the net B at the bottom, and we are going to send zeros and ones. That is your first 2 fault models, right? You have the top net is the aggressor, the bottom one is the victim, and in your first top line, you're going to send a 0 on A and 1 on B, and in your second one, you're going to do the opposite. So that's your two-way model. And then you flip the aggressor victims again, where now you make A as your victim and B as your aggressor, and you do the flip. That's how you get the four-way bridge model. And then everything is layout aware, right? So based on this, now they can create, extract your UDFM from your LDB file. For the again, for the same bridges, it's split between static and delay modeling. Static is just static zeros and ones, and delay model is going to send a 0 to 1 or a 1 to 0 on your aggressor and see whether your victim is going to be affected. It just has the same algorithm where the net A is the aggressor in the first two cases, and it becomes the victim in the third and fourth one. So this is the interconnect open extraction model. They have broken down the segment going from the Z output port on the left side. And you can see that it's broken down into segments S1, S2, S3, S4, S5, all the way to S7. And they're also keeping track of which vias come in the way in layout. And for each segment in layout, they're going to do the total critical area evaluation and then finally generate UDFM for both static and delay defects. So the ICO modeling is a lot more simpler, where once they figure out the segments and the vias in layout, now they're just going to send a static 0 or a 1 and see whether that reaches the receiver. And for delay model, they're going to do the opposite, do a transition instead of a static value. They're going to send a 0 to 1 or a 1 to 0. So that pretty much ends the introduction to defect-oriented tests and the interconnect bridge and interconnect open modeling. Now moving on to the evaluation on NXP automotive designs. First thing we wanted to show what is our current modeling for bridge defects. So for NXP automotive designs, we predominantly use a combination of NDetect stucket, NDetect transition delay, and like I mentioned before, we had already integrated the cell-aware stucket and cell-aware TD tests for the cell internal defects. And then we also do timing-aware ATPG, which is also called as small delay defects. Before we used to do path delay a long time back, but then we shifted to timing-aware ATPG, and SDDs are production pattern set for timing-aware ATPG runs. That provides a lot of coverage for all the front end of line, middle of line, back end of line, the standard defects. But for bridging, our model has always been to rely on the bridge coverage estimate that we get from our NSA and NTD ATPG runs. Because what we found is the number of patterns that were required using the older, the number of ATPG patterns that was required using the older traditional bridge models was just too high and not production friendly. So this was our convention. Again, we did not want to disclose what is the exact metric that we used, but it's a pretty high number. And like I mentioned before, the disadvantage with this metric is it was not layout aware based, and it has been holding really strong for the last few decades. So when this defect oriented test solution came from Siemens, we were very interested to go evaluate it on our designs. So here is just a quick summary of the UDFM extraction. Once we took a small design, try to flush this flow, we are showing the interconnect open extraction on the left for the number of opens that was actually extracted in our UDFM file, and the number of bridges is shown in the right. And what this graph shows is the number of defects in relation to the total critical area is shown, and it's in logarithmic scale. So what we can do is Tessent also provides the option to actually look at this histogram and pick which set of critical area do you want your patterns to be generated on. So this is we do an extraction for everything, and then we filter based on the histogram that we see to create a very high ROI pattern set for interconnect bridges and opens. And as far as the ATPG patterns are concerned, we decided to evaluate it on multiple designs, and we just put the bridges into interconnect bridge static and interconnect bridge delay, and we put the interconnect open ATPG pattern generation to the same ICOS and ICOD patterns. Then the coverage goals that we set, again, all of this is abstracted at a high level because we are not allowed to disclose the exact goals. Our traditional goals has been in the very high 90s for the traditional Stuckert and TD. So we just wanted to keep the total critical area-based coverage instead of the port fault level test coverage to be the same high 90s number. And here is a quick summary of the tester vector memory consumption. Because these tests are not cheap. They are very costly, and that's where the histogram also comes into play. So we took a small design to flush the flow. Once we flushed the flow, we started to go to the other end and pick a very big design B, which was actually a more efficient design because it was a much bigger design. And what we found is for the static comparison, the interconnect bridge static varied almost from 0.6 to 0.9% X increase in the vector memory, and the opens was varying from 0.4 to 0.6. For the bridges, it was way higher. It almost varied from 0.8 to 1.24 for the bridge delay patterns, and for the open delay patterns, it was like 0.4 to 0.95. Again, a lot of this depends on whether you're using hierarchical design or flat design, and how good your pin muxing is. So this was a good example to see where a small design and a big design will fall, and so that we can project our test times. Another summary is we just wanted to look at the complete inter-IC access where both bridges and opens are merged together, and what we found was the vector memory increase was it varied from 1.04x to 1.55x. And for the delay patterns, it was pretty close, almost 1.01 to 1.41. And our main focus from the defects that we have been seeing is with the ever-shrinking process nodes and the bigger automotive designs, while still trying to keep up with the zero DPPB goals, is the resistive defects were the ones that were becoming very challenging. So our primary focus or a lot of attention was being given to the delay model. Now here is a very high level view of the test program flow that we used. The traditional pattern set is shown in the left. We always start with traditional transition delay followed by Stuckert and the SDD patterns. And then we started adding our defect-oriented tests. Cell-aware TD and cell-aware Stuckert were already qualified. And then we started adding these new ICBD, ICBS, ICOD, ICOS tests. And all these tests were run across the tri-time, cold, room, and hard. And this was actually a delayed binning flow where every die is actually going to go run through every single test. Right? We did not bin out as soon as it failed, because this was more of a case study that we wanted to do. Then going over the silicon fallout data, I am not disclosing the exact amount of units that we did, but overall, this is the Venn diagram that we came up with. Let's review the static side first. You can see that there is not that much overlap with our traditional Stuckert patterns. And the biggest learning was we did not get a single unique failure from interconnect opens and bridge static patterns. So that is the right bottom thing that is shown in the diagram. And then if you come to the right side, we again started looking at the delay, and we had a very interesting finding that the bridge delay had 3 unique failures from this big data set that we ran for this case study on multiple designs. And we were theoretically hoping that a combination of the cell-aware tests and the interconnect bridges and opens will actually, totally fill in our traditional tests, but it is not actually. There was a lot of unique fallout for our, traditional NSA and NTD and STD tests. That's what we found. We are still working with, Siemens R&D team to see if we can make changes. But the key message from this slide is while paying attention and watching out for unique failures from these new tests, we were also trying to see how much of the new tests are actually overlapping with our traditional tests and potentially see if we can replace our traditional tests with the new defect-oriented tests. But we have our own theories because we do end detect on our traditional tests, which adds a lot of unique value. Coming to the silicon debug limitations, right now the unique fallout ATE characterization on the reject units is still ongoing. Again, all of this data is when we, on these reject units, we do a thorough characterization. And we did confirm that all our traditional patterns had very clean schmooze because the production test is just a point test. So we did a full CZ and made sure that the ICBD failing units had an elevated Vmin like they are shown here. And the suspect was potentially a bridging physical defect that was not caught by any of the traditional tests that ICBD patterns alone have modeled, and now it's adding value. So before we qualify any of our tests, we have to take it through full physical FA and really prove that it's a valid defect, because we have no room to, because most of the papers we have seen on defect-oriented tests, they stop here and they do not show the failure analysis results. So we are doing complete failure analysis on it, but it's still ongoing and we haven't completed that yet. And we did run into some limitations while doing this debug. What we found is we even checked with the Tessent Diagnostics R&D team, right? They said that while there is support for layout-aware diagnostics, chain failures, and gross delay diagnostics, for the bridge delay, there is no diagnosis algorithm for it built into Tessent. So we are collaborating closely with our Siemens R&D team, and we are feeding back our FA data to close the gap for bridge delay defects to enhance the diagnostics engine. And it's been a great partnership with the Tessent R&D teams from Siemens. So moving on to conclusions, from this case study, we finally concluded that the interconnect bridge silicon fallout data did confirm unique value added by the interconnect bridge test. And at least in this limited case study that we did not find any unique value addition from the interconnect open tests, but we are still evaluating more. But this is just based on this limited case study that we did on multiple designs so far. And based on these learnings and the unique value that was added by the interconnect bridge tests, we have started to enhance our 0 DPPB bridge coverage goals using the new interconnect bridge flow. And we did not show this data, but obviously while we were evaluating it for the first time, we did not want to directly start fault grading and only run top of patterns. So we just deployed the entire interconnect bridge and interconnect open pattern set. But there is a very easy opportunity to do fault grading from your traditional patterns and only do top of patterns and save a lot of vector memory too. So that is ongoing. And like I mentioned in the previous slide, there is very tight collaboration going on between our NXP and Siemens R&D team to add bridge delay diagnostic support. So with this, I'll also acknowledge the following team members from Siemens because we have had a very great working relationship with the Tessent team of Siemens. And me personally, I worked in 3 different companies, and my career pretty much is tied very closely to the Tessent R&D team. I've been doing this for the last 15 years, and it's been a great collaboration. And we really thank this opportunity to come here to give us the opportunity to present on this topic.